take the cart, we're going to move it up here and bring it to 100, and then while it's at 100, which is sitting right there, I'm going to come back and see what it's at. It's close to 100. It's 1.014, and what we can do is we can tell and correct the sensor and say, you know what? From what I read, it's exactly 1.0000 to 4 sig fig. So I press this button, and now it's exactly that. So what we want to do is we want to see if it's measuring properly. So I'm going to grab this guy. We're going to go as close as 30. And here's 30, as I see. So is it reading 30? It sure is, 31.2. Close enough. That's not bad. And then down here, it's going to go the whole way down to here and bounce off, and that's at 194, 194, and this guy is at 1.92. It's fine as long as it is consistent. So yeah, it seems to be an off a little bit just because of how this guy doesn't start at 0 right there, but it seems to work out pretty well. So we can see it at least. That's fantastic. That works. And then verify the motion sensor detects it the whole length. We did that. And then after we're finished, click fantastic. I believe this guy is, the sample rate is at 10 hertz right now. I'm trying to remember if I've made a mistake with could or could not. While the collision, I'm sorry, that's not 10 hertz. I was wondering why this is so slow. This is not 10 hertz. 10 hertz is 10 times a second. This is like once every other second, but that's just for testing. So if I go back here to measurements and click off of this guy, it'll stop doing that. But when we do measure it, it will measure it 10 times per second, which is what we want to do. So we're good. That's fantastic. I was getting kind of confused, but I'm easily confused. So we're at page 3 right now, and then off we go to page 4. We're so close. All right. Close the experimental setup window with the red X button. It looks like this guy. Here's the experimental setup button, and we're good. Close her up. Fantastic. Excellent. All right, so now what we want to do is we want to put a measurement display on the monitor. We had this last time when we did file open activity, but now we need to go ahead and create it. It turns out whenever we grab the motion sensor, it automatically brings along, this is the calculations and the measurements that this will measure. It'll measure position, and then based on position versus time, it will plot and calculate, or calculate and plot velocity. And then based on velocity versus time, it will calculate and plot acceleration. So these 3 things, it'll position, velocity, acceleration, and those are the things that we want to see, okay? So what we're going to do is we're going to click and drag the position entry, click position channel 1 and 2. This is channel 1 and 2 based on position. Fantastic. And drag that entry to the graph icon on the display section of the program, okay? So here we go. So we're going to go ahead over here to position. I'm going to left mouse click and drag, and I'm going to grab this down here to the display section where I'm going to go ahead and drop it onto the graph. You'll see there's a little plus button. It looks like I'm adding a file. If you were on Microsoft Windows, what I'm doing is I'm adding data to the graph icon. There we go, and there it is. Fantastic. Wonderful. Maximize the graph using the maximize button. Who would have thought? Here we go. Fantastic. So by default, the graph you just created has placed the position values on the y-axis, which is this guy, and time on the x-axis, which is that guy. Wonderful. Ensure that this graph has been created. If it's not, consult your instructor. I'm the instructor. We'll see what happens. Create a second graph by clicking and dragging velocity entry on the data window and hovering the cursor over any white space in the current graph. So what we want to do is we want to do just that. We want to grab velocity, okay, and click and drag it anywhere into our graph, but not anything special, not the axis, not at 4.5, not down here at 0, anywhere in the white space, and let it go. And now what it has done is it has added a second graph, and they both share the same time axis. So time axis on the bottom, here's the graph of velocity, and here's the graph of position. Fantastic. We did that. At this point, Data Studio program has been set up. Oh, I should have checked. Create a second graph, release the left mouse button, and the second graph should have created velocity on the y-axis and time on the x-axis. That's what we have. If a new graph has not been created, then figure it out. I think we're good. At this point, Data Studio is ready to go. That's all we need. So rather than, I know it says acceleration right here, and that's fine. We could just ask the acceleration. But what we're going to do is, rather than doing that, which is pretty simple, we're going to ask it to measure position as a function of time, and then use a calculation to find the acceleration. And we're going to use velocity as a function of time, and again, use one of our equations in a calculation to find the acceleration. So we're going to double check to make sure all of our equations are proper. All right. Screw the stiff spring accessory into the mounting hole of the accessory bracket. Put this down, run over here. That's what's here, that's already there. Here's another copy of it. Here's the accessory bracket. It's kind of cool, it goes in there. We have a stiff spring, stiff spring. That really is a stiff spring. A not so stiff spring. There's other accessories as well. This one I grabbed just to show you, doesn't have all of them. I can go over here and take a look at it. This guy, I believe, does. Here's the magnetic screen over here, and here's a hook, and here's a rubber bouncer, and here's a place for here's a place over here for some clay, some putty. We're going to be using all of these different types of bouncing materials when we study momentum in a little bit, but for now we just want the stiff spring, and that's good to go. So we're all set. Fantastic. Use the angle indicator to measure the angle of the tilt. I did that, and record this angle in the data table. I started that right. Move the collection cart to the start position of 30 meters, which is there, okay? And have one member of your group hold it there. I guess that's me. I'm a group of me. Have one of your lab partners, I guess that's me, place their hand behind the feet of the track so that it does not move during the collision with the accessory bracket. What that means is, depending on how fast this guy flies down here, if I'm not holding it, and I'll do the holding, what happens is sometimes it kicks this out, and we've had it kick this out, and of course it makes a big crash, just like that one falling down off the wall. This makes a big crash when it flies off the table. So we want to try to make sure that when this thing bangs into the spring, the rail stays put. We don't want some of the bounce energy, we'll be talking about energy in a little bit, to be lost. So I'm going to hold on to this guy probably from up there because I don't want it to move around. So I'm going to move this guy back up here. Here's the 30. Fantastic. Let's get this guy, and do I have, let's go ahead and do this once and see if this works. Did I move these guys back down? Let me see. Put these guys down all the way. Put this guy up. Okay. There we go. I can probably make this guy a little bit lower if I move this foot even closer down here. That's cool. Okay. And in fact, this guy is moving a little bit once I get it started again. So I push this guy here and I let it fly. Is it going to work or not? Let's just double check it. It's not moving very fast. It doesn't look like it's accelerating. It could be because the track is, it's not accelerating much at all. There it goes, there it goes, there it goes. That's really a not very impressive. There's the bounce. It's not very fun. Let me go ahead and switch this guy out. Maybe this guy over here happens to be easier. Let's see if this guy will do it. Okay, let her go. This guy's gonna roll a little better. There you go. I think that's more impressive. It looks as if this particular cart, for whatever reason, maybe its axles are dirty. Maybe I need to put some WD-40 inside there, or some, probably not WD-40, but put some graphite lubricant. Who knows? I'm going to swap those guys out. I'm glad I checked. But that's our experiment. What we're going to try to do is we're going to start it at 30, and I'm going to say 3, 2, 1, go. And we're going to watch. I'm going to hold it, but we're going to watch this thing fly down. It's going to go faster and faster and faster and faster and faster, and then bounce, go to the top, and then come back. And then it'll keep on bouncing until it's finished. So what we're really trying to simulate, if I use the ping pong ball, is we're trying to simulate me throwing it, not throwing up, but throwing it up into the air and then having it bounce. And then if it bounced several times, let me do this again. If it bounced several times, That's what we're trying to measure. So if I go ahead and do that a little bit faster, we're trying to measure that bounce. So bounce up to the top, stop and turn around, and then come back and bounce, and then it gets, again, this is a very, very shallow angle, so there's not much of a component of gravity pulling it down. So it's not a very fast process. It's not a very violent crash. It's kind of mild because it's just barely tilted, and these guy's wheels don't fly pretty well. But that's what we're trying to measure. We're trying to measure us taking the ping pong ball, shooting it up out of a slingshot, having it come to the top and stop, and then turn around and come back, and then do the bounce. So we're trying to measure that bounce. Okay, so let's go ahead and do that. So I'll put this here. There's no match score this time like last time. I start here at 30. Okay, and let's make sure I have this guy going here. Move the collision cart to the position of 30 centimeters on the track and have your lab partner, plus the start button on the data studio and release the cart. Press the stop button after the cart has collided with the spring for 2 or 3 bounces. Examine the data and make sure that we have some good data, which is here. Okay, we did good. That's page 4. I need to find page 5 because I think I have these guys out of space. There it is. And then we're going to analyze the data. It's pretty simple, and then we're good. So that's our experiment. So we've set up the experiment. The experiment is to let me make sure this guy's back here again because I changed that guy. Yeah, I really do see I see 1 degree. It's not a very huge significant figures instrument with a lot of precision, but let's call it 1 degree, which is fine. We're going to set this guy at 30. And again, we're going to let it go and see if it goes down. Fantastic. So let me go ahead and do that. Here we go. I'm going to press the start button over here, and then I'm going to manually press the stop button after it bounces a few times. So let's see what happens. So I'm going to press this button. We'll see if we get data, and then I'll move my camera so we follow this down here. So here we go. Okay, there's the data. I'm holding it. There's this guy over here. Nice bounce. There's our first bounce. This is the data we're trying to collect. There you go, and then I'll stop it. Okay, cool. Again, it's not very impressive, but if I go ahead and take this and make this a little bit larger, okay, we'll see that we get, I think I can move this down too. There we go. We can see that we get a bounce. Here's our cart coming down towards the spring. It then bounces and hits. Remember, the largest it could go was about 1.9 meters. That's what it says over here. It then bounces back and then hits, and then bounces back and then hits. So you can see that this is a bounce. It's sort of an upside down bounce, if you will, as if this were the ground. And then down here, looking at this data, if I make this larger, wow, that's really ugly data. Look how ugly this is. We'd love it to see if this was nice and straight for a constant acceleration, but you can see that the acceleration is not very constant. It looks like it had a real problem with this bounce. So let's see if we can clean this up. Here's our cart. I don't have any lubricant, unfortunately. I'm going to go ahead and use the old finger trick again to see if I can get some of the dust out of there. Just going to go ahead and see right away if we can make this guy any better. And maybe we'll get better data as this guy goes. So back down, I'm not collecting data. Back up, and then back down. I don't know if that's any better, but we could try it. So let's try another set of data. Because I'm not suggesting that this is bad data, so I should get rid of it because I don't think it will agree with my hypothesis. I just don't think it should be a nice parabola, and this seems like a goofy squished parabola. So what I'm going to do is I'm going to go to experiment, and I'm going to go to delete last data run, and it makes this data disappear. Fantastic. And then I'll run it again. So let's see if I can get this guy to run again. On this time I'm going to just let it go and see if it works. So here we go. So press start. Okay, it's running down again. There it goes. Come on, give us a good bounce this time. There's a nice bounce. Stops. Goes back again. There's a nice bounce. Come back to here, and I stop it. You know what? It's just the data's the data. How's that? It looks like this is what we have with our data up here. If I make this larger and bring this back down again, there's our bounce we're worried about. Here we go. That's the bounce we want. We want the first bounce. It does look like that it's off a little bit, but you know what? It is what it is. We're going to take the data as it comes. We're going to move this guy down a little bit like this. Okay, move him down. Come on, you can do this. Here we go. There we go. All right. So what we want to do is this really should be a parabola, because the parabola is what the shape is when we have position versus time, when something is moving with constant acceleration. And this should be a straight line when it's moving with time. Again, that's really, let's see what the data says. Maybe we'll save ourselves. So what I want to do is over here is I want to see what we're going to do. I want to fit the data up here to a quadratic. A quadratic model is what we use to fit a parabola. Okay, it's a quadratic. It looks like the quadratic equation with an a and a b and a c, which is exactly what the negative b plus or minus b squared over negative b. What is it? B squared plus or minus the square root of b squared minus 4ac over 2a. That guy. If I said it long enough, it's that guy. So that's the quadratic equation, and that's the quadratic model. So let's go ahead and do that. I want to select just the data that's in that region, which looks like this. Okay, there we go. And I go over here to fit, and I'm going to grab a quadratic fit. And here's our guy. And we can see that the mean squared error is 3.2 e to the minus 4. That's kind of, again, it's small. That's e to the minus 4, so there's lots of zeros. It's 0.0003, so it matches pretty well. But you can see it's sort of squished, but because it's squished high over here and it's squished low over there, it may be that even though our data does not look perfectly symmetric, we might get some good data. Again, this is how it's useful to get data from the laboratory, and even though it's not perfect because of all these things that are happening, we still can get some pretty good results. Let me go ahead and move this guy up a little bit. There we go. Fantastic. So with that, I want to record this A term, the 0.0621. That's what we want. So I want to record the A term of our